Today we're going to discuss 4.2 null spaces, column spaces, and linear transformations. Null space. An m by n matrix A, written as null A, is the set of all solutions to the homogeneous equation ax equals 0. Null A is A such that x is in Rn and ax equals 0. Theorem 2. The null space of an m by n matrix A is the subspace ax equals 0 of m homogeneous linear equations in n unknowns in the subspace of Rn. Equivalently, the set of all solutions to a system ax equals 0 of m homogeneous linear equations in n unknowns in a subspace of Rn. Let's look at example 1. Find the explicit description of null A when A equals this matrix here. So the first thing we want to do is we want to get this into reduced echelon form. So we're going to take this matrix here, matrix A, and get this in reduced echelon form. So the first thing I'm going to do is I'm going to take negative 2 row 1 and add it to row 2. So row 1 is going to remain the same. I'm going to take negative 2 row 1 and add it to row 2 to get 0, 0, 1, negative 6, negative 15. Then I'm going to take 1/3 of row 1 to get 1, 2, 2, 1, 3, and not do anything to row 2 for the time being. My next step is I'm going to take negative 2 row 2 and add it to row 1, so this becomes a 0. And we are now in reduced echelon form, since we have a pivot row here and a pivot column here and pivot column here. And we have a 0 above this one, 0 below this one. So my system of equations would be x1 equals negative 2x2 minus 13x4 minus 33x5. x2 is a free variable. x3 would equal 6x4 plus 15x5. x4 is free, and x5 is free. So then we would write x as x2 times negative 2, 0, or negative 2, 1, 0, 0, 0, plus x4 times negative 13, 0, 6, 1, 0, plus x5 times negative 33, 0, 15, 0, 1. If I were to call this vector u, this vector v, and this vector w, this would equal x2 times u plus x4 times v plus x5 times vector w, and null A would equal the span of u, v, w. Since every linear combination of u, v, and w is in an element of null A. So let's look at some observations. 1. Span and set null A found using the method in the last example is automatically linearly independent. Because C1, C2, C3 end up being 0. 2. If null A doesn't equal 0, the number of vectors in the span and set for null A equals the number of free variables in AX equals 0. Column space. The column space of an m by n matrix A, column A, is the set of all linear combinations of the columns of A. If A is A1 to AN, then column A is the span of A1 to AN. Theorem 3. The column space of an m by n matrix A is a subspace of Rm. Recall that if AX equals B, then B is a linear combination of the columns of A. Therefore, column A is vector B such that B equals AX for some X in Rn. Example 2. Find a matrix such that W equals column A, where W is X minus 2Y, 3Y, and X plus Y. X and Y are in R. So we need to write W as a linear combination. So W is going to equal X times 1, 0, 1 plus Y times negative 2, 3, 1. Therefore, this equals the span of 1, 0, 1 and negative 2, 3, 1. What we're going to do is we're going to use vectors in the span and set of columns as columns of A. Then W equals column A, and you're done. So with this, you need to recall Theorem 4 from Chapter 1. The column space of an m by n matrix A is all of Rm if and only if the equation Ax equals B has a solution for each B in Rn. So that's something that you need to recall for this one. Let's look at example 3. Let A be this matrix. A, the column space of A is the subspace of Rk, where K equals, and hopefully you have 4, the number of rows, equals the number of variables. B, the null space of A is a subspace of Rk, where K equals 3. This is X such that Ax is defined, must have 3 entries. So we must have 3 entries for this. Now C, find a non-zero vector in column A. There are infinitely many possibilities. So there's many possibilities. However, find a non-zero vector in column A. We can just use the first vector, 1, 2, 3, 0, that column there. And then D, find a non-zero vector in null A. So that means we have to solve Ax equals 0 and pick one solution. So we have A up there, and we need to write A and find a solution for A when it's set equal to 0. So we have 1 and when this equals 0. So 1, 2, 3 equals 0. And then when 2, 4, and 7 equals 0, 3, 6, 10, 0, and then 0, 0, 1, 0. So the first thing I'm going to do is I'm going to take and have negative 2 times row 1 plus row 2 to transform row 2. I'm going to take negative 3 row 1 plus row 3 to transform row 3. And when I do that, row 1 is going to stay the same. I'm not going to do anything to that. The first thing I'm going to do is I'm going to take negative 2 row 1 and add it to row 2. And I get 0, 0, 1, 0. The next thing I'm going to take negative 3 row 1 and add it to row 3. And I get 0, 0, 1, 0. And my last row, I'm not doing anything to. Next, coming up here, I'm going to take negative 3 row 2 and add it to row 1 to get 1, 2, 0, 0. I'm going to leave row 2 alone. And then I'm going to take negative row 2, add it to row 3, and same thing, negative row 2, add it to row 4. So with this, we only have x1, x2, x3, okay? So x would equal x1 equals negative 2x2, x2 is free, and x3 equals 0. Therefore, x would be x2 times negative 2, 1, 0. And x2 should have 3 entries, so that is our one solution, negative 2, 1, 0. Contrast between null A and column A, where A is an m by n matrix. So you can see page 332. I'm going to review that. A subspace of a vector V is a subset of H of V that has 3 properties. The first being the 0 vector of V is in H. The second one, for each U and V in H, U plus V is in H. In this case, we say H is closed under vector addition. And C, for each U in H and each scalar C, Cu is in H. In this case, we say H is closed under scalar multiplication. And if the subset satisfies these 3 properties, then H itself is in the vector space. So see theorems 1, 2, and 3 in sections 4.1 and 4.2 if you need to review it. So let's look at example 4. Determine whether each of the following sets is a vector space or provide a counterexample. So H, X, Y is our vector, and then we have there X minus Y equals 4. So looking at this right away, this is not a vector space because you cannot get the 0 vector ever. So not a vector space because you can't get the 0 vector. Let's look at B. B says V is XYZ, where X minus Y equals 0 and Y plus Z equals 0. So this one, let's see if we can get the 0 vector. And XYZ is the null space, or null A, which is the subspace of R2. Therefore, it's in the vector space because we can get AX equals 0. So this is in the vector space. And the last one, S, we have X plus Y, then 2X minus 3Y, and 3Y, and X, Y, and Z are all real. So let's go ahead and rewrite this, and I believe we could get the span of this being columns A. So we have X is 1, 2, 0, plus Y, 1, negative 3, 3. This equals span of 1, 2, 0, and 1, negative 3, 3. Since this is column A, therefore S is in the vector space by theorem 1. So you can say S is in the vector space, and that's by theorem 1. Kernel and range of linear transformations. Linear transformation. A linear transformation T from a vector space V into a vector space W is a rule that assigns to each vector X in V a unique transformation X in W, such that first, the transformation of U plus V equals the transformation of U plus the transformation of V for all U and V in V. Second, the transformation of C times vector U is our scalar C times the transformation of U for all U in V and all scalars C. Kernel, also known as the null space of T, is the set of all vectors U in V such that the transformation of U equals 0. The range of T is the set of all vectors in W of the form transformation of U where U is in V. So if the transformation of X equals X, column A is the range of T. So with this, you can say column A equals span A, and the range equals column A.